Okay, welcome to your lecture on section 6.3, step function. Okay, so some of the most interesting elementary applications of the transform method occur when the forcing function for our differential equation is discontinuous or impulsive. And equations of this type frequently arise in the analysis of the flow of current in electric circuits or the vibration of mechanical systems. To deal effectively with functions that have jump discontinuities, we need to sort of have the most elementary jump discontinuity as a model, and we do so by using the unit step or Heaviside function, which was developed by a gentleman named Oliver Heaviside. This function is defined by u sub c of t, which is 0 when t is prior to c, and 1 when t is greater than or equal to c. So if we draw a graph of this function, it's really just a function that is literally nothing until you get to c, and then it's 1 thereafter. And these types of functions serve as the building blocks for discontinuous functions. Okay, so for a given function f, for example, if we want to have this function sort of turn on at a given point and be off before that point, what we can do is model that using a piecewise defined function. So call this thing g, say it's 0 when t is prior to c, and then f of t minus c when t is greater than or equal to c. So all this is doing is taking, let's say, a function like this and moving it over c units to the right. We can more easily write this thing without this sort of piecewise framework by just using the unit step function or Heaviside function centered at c. If we do so, it has the same effect. If t is less than c, then the unit step function flashes 0, which means that g is 0, which is exactly what g is there. And if t is greater than c, then u of c is just 1, and the function becomes f of t minus c, which is exactly what g is here. And the reason this formulation using the Heaviside function or the unit step function is advantageous is that instead of having to do multiple integrals using the definitional Laplace transform, we can use this theorem, which says that if the Laplace transform of f exists, then the Laplace transform of the unit step function centered at c times f moved over c units is just the Laplace transform of f times this discount factor e to the minus cs. Okay, and that's valid for all s greater than or equal to a, which was the supposition above here. And then conversely, if you're trying to take the inverse Laplace transform of e to the minus cs times something you know the inverse Laplace transform of, you end up with the function f moved over c units times the unit step function centered at c. So for example, if we're looking at the Laplace transform of sine of t shifted over to the right pi units times the Heaviside function centered at pi, the discount factor is e to the minus pi s, and then we multiply that by the Laplace transform of sine of t, which we know is 1 over s squared plus 1, and so the entire Laplace transform is given as e to the minus pi s times 1 over s squared plus 1. And oftentimes we're going to try to do inverse Laplace transforms. If we started out here at this end, we could see that this is just something we know the inverse Laplace transform of times a discount rate. We can go all the way back, as in the second part of the theorem, and say, okay, well, it's just going to be sine of t shifted over pi units, because there's that pi there, multiplied by the unit step function centered at pi. Okay. Another theorem says that if we know the Laplace transform of f exists for s greater than a, and if c is a constant, then taking the Laplace transform of e to the ct times f is going to give us the Laplace transform of f, but shifted to the right c units in the complex frequency space. And conversely, if we want to take the inverse Laplace transform of the Laplace transform of f shifted over c units to the right in the complex frequency space, we end up with, in the time domain, f, and then multiplied by some sort of like surplus factor e to the ct. So for example, if we're trying to find the Laplace transform of e to the 2t times t squared, we know that since the Laplace transform of t squared is 2 over s cubed, that now we're going to have 2 over s minus 2 cubed because there's this 2 here, the surplus factor there. Okay, thanks for listening.